Добрий день, колеги. Наш день учим за gravitaционные волны. So, welcome. Thank you for coming to my classroom. I'm excited to have you all here. It's been a pretty big week as far as discoveries in science. And I'd like to share with you some of the revelations and some of the discoveries that have just recently occurred in the field of physics and astronomy. So, the discovery or direct observation of gravitational waves has occurred for the first time. And the paper published in Physical Review Letters entitled Observation of Gravitational Waves from a Binary Black Hole Merger is not only the first time we are detecting gravitational waves, but also the first direct evidence of the merger of two black holes. And so this is a really exciting point in history. I'm going to use the allegory of the cave for a moment from Plato's Republic as I proceed. And if you would bear with me for just a moment, I'd ask that you think about having lived your entire life inside of a cabin. You've lived your entire life inside of a cabin, and all you know is the viewpoint you have from a single window. All you know about the natural world outside is through that one single window. And you've learned a lot. Let's say, for example, that this window is facing north. And you've been able to observe the natural world through this window, and you know, for example, there's something that's generating a tremendous phenomenon, a tremendous quality that allows you to observe and see the universe around you. And I'm speaking about light. But you've never been able to see the sun. You've never been able to see the sun directly, but you know there's something there. Okay? Now imagine during your frustration of being confined on the interior of this cabin that you find a pair of binoculars. And suddenly, using this tool, using this apparatus, you can learn so much more about the natural world outside. You're able to look further, you're able to scrutinize in more detail. So much information has now come to you thanks to this tool that you've discovered. And then suddenly you discover a hidden door. But that door is locked, and all you can do is look through the keyhole. And you're looking in a completely new direction, a completely new view on the universe, but it's just the view you can see through that keyhole. And this is an analogy talking about what this discovery and its ramifications will have on our ability to observe the universe. Because we are trapped in that room. We have been trapped here on the planet, and thanks to the discovery and the technology, Galileo first looked through the telescope in the 17th century. It gave us a whole new perspective on the universe. It said that astronomy is a humbling science because it puts you in your place. And so the direct observation of gravitational waves is something that we're really excited about in physics and astronomy. And I want to start off with a brief definition. A gravitational wave are dynamic perturbations or a ripple in the fabric of space-time which propagate outwards at the speed of light. And the speed of light isn't so much about the speed of photons, it's more about causality. How quickly or how fast can information be passed through the universe? How quickly can information, how readily is space-time able to communicate with itself? This revolutionary theory, the theory of general relativity, was proposed by Albert Einstein in 1915, 10 years after working and publishing his original, hello, welcome, his original treatise, Physica, and the theory of special relativity. And what came out of this new theory was that our perception of gravity is an illusion. The things that bind me to the ground, the things that bind all of you to your seats, is actually an illusion. It's not a force acting on us. It's us as massive objects following the curvature of space-time. And so all objects that have energy, that have mass, warp the fabric of space-time. and we follow along on this curvature that keeps us glued to our seats. I have this wonderful video, and I'd love to eventually get enough of spandex. As a rower in college, I was intimately familiar with spandex, okay? But I never had this much spandex that I could stitch it together to create a two-dimensional representation of the warping of space-time. And so this teacher has taken several sheets of lycra, a type of spandex, and has stitched it together and then pinned it on a very large ring so that he could create a surface in which to place massive objects to distort or give an analogy for the warp of space-time. And he's going to, in a moment, just place two massive objects, and you're going to see how these two massive objects are attracted to each other due to that warping.
I have another object, it also warps space-time. They feel that, and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. And if you have more mass,
He eventually puts a large massive object in the center and then does an example of how solar systems are formed. As the molecular cloud collapses and a gravitational well is formed at the center of this molecular cloud, he's going to go ahead and toss a bunch of marbles, and it shows how the conservation of angular momentum due to the elimination of variation in the flow circling the mass. So he's going to go ahead and toss a bunch of marbles. Okay? He's going to go ahead. And you're going to notice how the marbles cancel each other out until there's one preferential direction of rotation. And this is an example of how solar systems form. Okay? How planets end up forming around a massive star. And one of the coolest things he does in this video is he eventually gets a little marble to orbit around a larger marble. And it's an analogy for the moon orbiting around the Earth and the Earth orbiting around the sun. He's going to give it a toss here in just a second.
leaning against the table underneath fixing holes from last year. One time my principal walked in, and I hear somebody in, and then he's looking around. Often he gets to say that. And sometimes and so when we went to the moon,
Sorry.
he's looking around. And so you can see that this.
There we go. He gets one little marble to orbit around another marble. And so even the Earth itself warps the fabric of space-time and keeps the moon bound in its orbit around the Earth. And this is an elegant, absolutely elegant visualization of the curvature of space-time, but only represented in a two-dimensional object. And so you have to extrapolate, you have to think about this occurring in 3 dimensions and occurring throughout the entire universe. Yeah, absolutely.
So here we're seeing it like sped up dramatically, right?
No, not
the actual video itself, but like if that was planet Earth orbiting the sun.
Oh yeah.
Because all of them end up colliding in the middle.
Yeah. Well, you're looking also at a system that is losing and dissipating energy due to friction between the marble itself and the fabric, whereas while energy can be dissipated due to the radiation of gravitational energy. For example, in the solar system, that rate of loss is so slow that planets essentially stay consistent in their orbit through billions of years. And so there are several major predictions that Einstein had concerning general relativity. One of them was gravitational lensing, that light itself would be bent around massive objects. And when we look out into the universe, particularly with the Hubble Space Telescope, we've seen this warping effect. And unfortunately, I didn't bother to add this image to So we have this gravitational lensing effect because of the curvature of space-time. And so a distant galaxy that may be obscured or blocked by a more a closer galaxy, the light will actually bend around, and we will sometimes see one distorted image of that particular galaxy, or maybe several variations or examples of that galaxy surrounding a central massive object. A couple other major predictions that Einstein had was gravitational time dilation. And this was confirmed when we started putting satellites up into orbit. The deeper you are in a gravitational field, the slower time passes for you relative to an external perspective. And this is kind of big, because when we get really close to a black hole, and I'm talking about approaching an event horizon, time slows down to a standstill. And there are some pretty unique concepts about what it would be like to enter a black hole that I'll talk about in just a moment.
How are they measuring the difference in time passage between two satellites? I mean, is it literal? I mean,
you're also getting into relativistic time dilation. The faster you travel, relative to an external perspective, time slows down also for you because of that cosmic speed limit, the speed of light. The whole internal mechanisms for subatomic particles actually slows because the speed of light has to be conserved. And if I'm traveling at even 1/10% of the speed of light, I'm going to notice a significant time dilation if I were to compare it to a person here on Earth. That's the twin paradox. Two twins, one twin on Earth, another travels off into a spaceship, and when that spaceship comes back, the twin on Earth has aged significantly more than the twin that went off in the rocket. And so the space-time curvature is something that we can measure, and this is what we're going to be talking about when we are talking about the detection of gravitational waves. It's this ripple in the fabric of space-time that we're measuring. And this measurement is significant, it's absolutely significant, because alright, I'll talk about stellar remnants briefly, and then I want to show you a scale model of the universe. So stellar remnants. Stars evolve through their life depending, their primary characteristic is their mass, and the primary unit for mass that we use for stars is a solar mass, so the mass of our sun. And so for a low mass star will go through an evolutionary cycle that leads to a white dwarf. Our sun is destined to become a white dwarf in 4 billion years, 3.5, 4 billion years, okay? For a large mass star will evolve into a red supergiant, eventually go supernova, and depending on the mass of the stellar core, the core inside that star, it will either evolve into a neutron star or a black hole. And that threshold is for a stellar core is about 2.8 solar masses. Okay? This is where the outward pressure due to neutrons pushing against each other is overcome, and literally matter collapses in on itself infinitely down into a singularity. And so a black hole is a type of stellar remnant, a geometrically defined region of space-time, the singularity and the event horizon. The singularity is at the center of a black hole. The event horizon is the surface you can think of. It's not really a surface, but it's where the escape velocity is equal to the speed of light. And so even light itself can't escape from a black hole. And the curvature, if I was to talk about that spandex analogy, that well, that gravitational well that's created by this mass would extend infinitely downwards in this example, so that nothing can escape. And it collapses down into that singularity. Okay? And so I'm going to take a moment. The LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 observatories, one in Hartford, Washington State in the United States, and one in Louisiana. And they detected on September 14th of 2015 a disturbance in the gravitational field. Okay? And this telltale disturbance signaled the passage of a gravitational wave. And it matched so incredibly accurate to the theoretical calculations for the merger of 2 stellar mass black holes. That's 2 black holes that have relatively about 60 and 30 solar masses. 30 and 60 masses of our sun. Okay? And so to kind of impart the gravity of this measurement and its significance, I'd like to just dive into the scale of the universe for just a second. Okay? We are detecting 1/10,000th of a femtometer. A femtometer is roughly equal to the size of a proton. And so we are measuring a fluctuation in the curvature of space-time that dives down to 10 to the negative 15, 1/10,000th of 10 to the negative 15, down to the femtometer. And so we are detecting variations, wobbles in the fabric of space-time that is only 1/10,000th the diameter of a proton. Okay? And if I were to zoom back out, we are detecting this merger of two black holes 12 yoctometers. Okay? 10 to the 24th, which is just about half a megaparsec. Actually, just a little bit further out here. I gotta keep going. I gotta keep going. It's easy to get lost in the universe, folks. Okay, and so I'm getting there. I'm close. We're larger than the Virgo supercluster. There's the ionometer. Okay, and so we are measuring. Where's the megaparsec? Gigaparsec. There we go. So 400 megaparsecs away is the merger of this two black hole. So we are measuring something so incredibly far away on the very smallest of scales. And so this is a huge accomplishment. Not that the engineering involved with the LIGO detector isn't on the scale of the engineering for the CERN, the Large Hadron Collider, but it's a $250 million observatory that was funded by the National Science Foundation in the United States. And so the basic detection for, this method, we are using highly coherent light. Okay, a light source that has the exact same frequency coming from, let's say, a high fidelity laser. Okay, and that laser is shining down 4-kilometer long evacuated tubes. So these tubes, this stretch of the arm and this stretch of the arm, are 4 kilometers long. And as the gravitational wave passes, it's going to compress one of these arms and stretch the other arm. Okay? And we're measuring the strain. Strain is the mechanical deformation of a material, and we can measure it by measuring its deformation over its original length. And so the best example I can talk about is if I were to stretch a rubber band. As I stretch that rubber band also gets a little thinner in the middle. And this rubber band is undergoing strain. And that's what's happening to the Earth as these gravitational fields are passing by. The Earth is being stretched 10 to the negative 15th, or actually 10 to the negative 20th in one direction, and slightly made skinnier in another direction. And so using this interferometer, we can bounce lights off mirror, and we have a beam splitter that part of my apologies. So light is coming from the laser. It passes through the beam splitter, and that beam splitter then passes part of that laser to the mirror. It bounces off the mirror. It bounces off the secondary mirror, and where they meet, we can get an interference pattern in the light. And it's the study of this interference pattern, how the peaks and crests and the troughs of this light align, that allows us to measure the strain in the light. Okay? The strain being exhibited in this detector.
Because the tubes have changed.
The tubes have changed length. One tube has gotten compressed slightly, and one tube has gotten stretched slightly on the smallest of scales. And this detector, noticing the change in the interference pattern, Interference was first observed by Thomas Young in 1801 and demonstrated the wave-like behavior of light. And so we have a waveform, wave fronts traveling through a double slit experiment, creating an interference pattern. And this telltale brightening and dark fringes is what we refer to as an interference pattern. And it's by analyzing this interference pattern that allows us to determine the gravitational wave-induced strength.
How quickly, I mean, what's the time duration of that disturbance? How fast was it here and gone?
And so it's about 2.5 seconds for this disturbance to pass by. And the time between measurements is about 0.007 seconds. And that corresponds to the speed of light between the distance between these two detectors. And so 3 solar masses from the collision of these 2 black holes were converted into gravitational energy. That's a tremendous amount of energy being released. The sun will convert approximately 1% of its total mass into energy through its 10 billion year long lifespan. And if we were to multiply that, it would take the sun approximately 1.5 trillion years to radiate that much energy that's released in the course of 2.5 seconds through the merger of 2 black holes. And so if we could view the merger of these 2 black holes in the electromagnetic spectrum, it would be brighter than all of the light coming from all of the stars in the observable universe. It's that powerful of event. It's the largest measured release of energy outside of the Big Bang. Okay? And so the historical significance is, again, if we go back to that analogy of the cave, for example, we are opening a whole new window by which to study the universe. We're opening a whole new doorway that will allow us to look and study the universe in a completely new spectrum that we haven't been able to use before. And as the technology and the resolution and more observatories are generated, like the evolved laser interferometer space antenna, ELISA, which is planned for 2019, we will be able to start making measurements and studying the universe through waves of gravity. I'm going to allow Brian Greene, author of An Elegant Universe, summarize.
Tremendously exciting news. Gravitational waves have finally been detected. Here's a brief explanation. Back in 1915, Albert Einstein gave the world his new theory of gravity, the general theory of relativity, which is based on the beautiful idea that gravity is nothing but warps and curves in the fabric of space-time. Now, barely a year later, Einstein pushed this idea one vital step further. You see, he realized that if space is flexible enough to warp, then it should also be able to ripple, to vibrate, to undulate. And that would mean that if something were to jostle the fabric of space-time, it should send out ripples in the fabric of space, and it's those ripples that we now call gravitational waves. Now, of course, the source of gravitational waves would not be my hand jostling space. Instead, it would be some highly energetic astrophysical process like rapidly orbiting neutron stars or black holes that would send out a steady rumble of gravitational waves. Or at least, this is what the theory says should happen. Now, how do you test this idea? Well, the math shows that as a gravitational wave rolls by, it will squeeze and stretch anything in its path. You see it happening here for the Earth, but of course, this is highly exaggerated so you can see the effect. When you do the calculation, you find that the amount of squeezing and stretching would be tiny, a mere fraction of an atomic diameter, and that makes it pretty difficult to detect. But that is what the LIGO team has now achieved. And they did it with 2 detectors, one in Louisiana, the other in Washington State. And in these detectors, what they do is they fire laser beams along 2 4-kilometer-long evacuated tunnels. And when the light recombines, it creates an iconic pattern. It's known as an interference pattern. But the only thing that you need to grasp is that were a gravitational wave to roll by, It would squeeze and stretch the arms of the detector, and that would have a measurable impact on that interference pattern, causing it to shift. And it's just that kind of shift in the interference pattern that the LIGO team has now observed, the first direct detection of gravitational waves. And this is big. This will go down in the history of science as a pivotal moment. And not just because it's another spectacular confirmation of Einstein's ideas, which it is, but rather because for millennia, we have explored the universe using waves of light. This discovery marks the opening of a new era in which we will explore the universe using waves of gravity.
That concludes my discussion. If you folks have any questions, I'd love to be able to try to answer them. I, as a science teacher, love good questions, and there are a couple pieces of paper and pencils distributed around the room. If you have any questions that you'd like me to answer via email, I think I'm going to be sending out an email later this evening with a bunch of sources and links that if you want to go down the proverbial rabbit hole, you can. And if there are any commonalities or trends in the questions, I'll do my best to field any frequently asked questions, or I can answer questions now.
Have these detectors ever detected any disturbances before this one? I mean, have they detected small ones and then the big one, or was it just 20 years of nothing and then this?
Well, the original design for LIGO was released in 1974. It's a joint venture between Caltech and MIT. Construction started in '92, and it was operational from 2000 to 2010 with no detection, no measurable signals. And from 2010 until 2015, LIGO went through a renovation, and it's now called LIGO, Advanced LIGO. And they literally booted up in the beginning of September, and on September 14th, they discovered their first hit, first measurable signal. And so the resolution went from 1/1000th of a femtometer to 1/10,000th of a femtometer. And so it's went up several orders of magnitude as far as their ability to detect these gravitational waves. And so it's pretty exciting.
Was it recorded by other teams all around the world?
Well, the detection originally occurred in September 14th, and they stayed quiet all the way through the new year. The LIGO team regularly sends false signals through the detector to constantly keep the researchers on their toes to make sure that they're processing signals in the most appropriate method. And so they sat on this for approximately 4 months until they knew that the science was sound. As LIGO, there's only one other interferometer that could possibly detect. It's the Virgo in Italy. And so this one, Virgo, was down during this detection. And so validating this particular signal is kind of impossible because those waves of gravity have passed us by. But I think we're going to continue to see, due to the advanced LIGO and the Virgo and eventually ELISA up in space, we'll be able to continue to see more and more of these discoveries occur.
Chris, and I'm just curious, what will happen if we, for example, Earth is closer than this anomaly, merging of two black holes? Are we going to be stretched a lot more or something?
You're thinking about a weight loss program?
No.
Yeah, we definitely...
If this happened closer to Earth,
yeah,
what will happen to Earth?
Well, what would necessarily happen, like, it depends on the proximity. The gravitational energy, just like light, dissipates due to the inverse square law. And so, just like gravity, the further you are from the source, the weaker the force of gravity you feel. And so anything that would occur in our own galaxy, the merger of two black holes within our galaxy, would definitely have a more significant effect. Would it cause any type of disturbance to life on Earth besides everybody getting a little, I don't know. That's a tremendous question, and I don't know what the biological or the physical effect on humans would be if it was really quantifiable as far as our human experience.
Yeah.
Can you expand a little bit on the formation of the black hole? Because I've never read about it. So you said basically the neutron attractive force are overcome by...
Yeah, the stellar core overcomes the neutron degeneracy pressure, in which the outward pressure from neutrons can no longer stop the inward collapse of gravity. And so,
Because usually when you think of an explosion, you're talking about an explosion of this white dwarf or supernova.
so we have,
But you usually think of expanding forces, not imploding.
Yeah.
I want to see where.
well, a supernova is a three-dimensional ricochet off the super dense stellar core. And so, as soon as a star tries to fuse iron together, so iron is constantly building up in supermassive stars. It's a process of nucleosynthesis, stellar nucleosynthesis. And so we have this concentric ring, it's kind of like a nested Russian doll of heavier and heavier elements being produced. But as soon as the pressure and temperature inside the core of this massive star is great enough to try to fuse iron together, that's an endothermic reaction. That fusion reaction is an endothermic reaction. Starts to absorb all the extra energy in the interior of the star, and the whole fusion process shuts down. And so gravity suddenly wins in those milliseconds, and the star collapses in on itself, but the core is so dense, it acts like if I were to take a bouncy ball and a ping pong ball and I drop it. The bouncy ball would bounce off, and then the ping pong ball would go shooting up into the air. Okay, and that's a really simple analogy of what's happening in 3 dimensions, is all of this stellar mass collapses down on the core and then ricochets and bounces outward in the supernova. And depending on the pressure and temperature during that inward collapse is what's going to either cause the massive star to evolve into a neutron star or a black hole.
And when these two black holes are merged, what happens? One big black hole?
One larger black hole with a greater radius for its event horizon will form. But so, like 3 solar masses are dissipated in the collision of these two particular black holes. So imagine if I could convert using Einstein's famous equation E equals mc squared. If I can convert all of the mass of the sun, that's like 10 to the 30th kilograms. If I could convert all of that mass of the sun into energy, 3 times that was the energy released in these gravitational waves. But because it's so far away, by the time it reaches us, it's almost unimaginably small.
How often do these events happen?
So, 2 black holes colliding in our own galaxy would be a 1 in a 10,000 year event. But
it's soon.
yeah, that's
It sounds very soon.
doomsday. Probably Mr. Young. We can only see about the volume of about 1%, a little less than 1%, about 0.8% of the observable universe is detectable through this LIGO observatory. So we can only see a fraction, but that's well more than enough to have millions of galaxies in our collection, or our ability to collect information.
Does this mean, Chris, that this observation and measurement was planned? They expected these 2 black holes to merge?
No, I don't think we
So
can.
how did they identify that this comes from this?
Yeah, how can you see that far away?
Let's go to the data.
Oh.
And so, here's your answer. Just go ahead and read this. So we're measuring the strain, and here is the mathematically predicted disturbances or gravitational waveforms that is generated by the field equations, Einstein's field equations that he released in general relativity, and here are the observed patterns. Now this from the Livingston, Louisiana Observatory is inverted and shifted due to the geometry of the observatory itself and its distances. But you can see that the data, or the oscillations we're seeing here, align successfully. And so this isn't some type of seismic event, this isn't some type of vibration due to passing traffic, because both of these signals were detectable 0.007 seconds apart, which would correspond to the propagation of the speed of light between these 2 detectors. And so we're measuring the strain 10 to the negative 21st. And again, remember, strain is the measure of the mechanical deformation of an object, how much it's being stretched in one particular direction. And so we're measuring the stretching and compression of planet Earth with these two detectors.
So, Christian,
Did that answer, wait, who? Did that?
Yes, how do we know that it was that it came from those two black holes though? Like, can we see that far into space? Do we know? Like,
No.
How do we know that happened?
But we can, all right, so we have a general direction, we know a general direction based off of the geometry of how these two observatories are aligned. But when we have 3 or 4 observatories, now we can start triangulating and pinpointing exactly maybe what galaxy this collision is occurring in. Right now we don't have the resolution to be able to determine that, but we can calculate its distance based off of looking at the math, and I'm sorry, but I'll have to admit the math is beyond me. It's well beyond my capabilities. I dived into it looking at it, but theoretically the expression of what two black holes would look like as they merged, as they degraded in their orbit. I have a visualization of what this would look like using neutron stars. I was not able to, oh shoot, I may have closed it.
so Christian, while you're looking, we can figure out how big this event is. We can figure out where it's happening. And do we just have to assume that it's two black holes interacting in this way? Is that the only way we can account for something this size?
Yeah, if we look at the variables that come out, there has to be something in the order of 60 to 30, for this particular example, 60 to 30 solar masses, okay, 30 to 60 suns, if you will,
Right.
and they're only about 200 kilometers apart when they merge.
Okay, so this is really, it's not like we know that it's two black holes, it's just the only way we can account for these waves, even just getting here.
They're heralding this as direct confirmation of the existence of black holes, direct observational evidence of the existence of black holes. And if my ability to explain it is a little lacking, my apologies. But again, if you would like me to send you an email, I'd love to put together a list and send you all down the rabbit hole, because you could spend another half hour, 40 minutes learning.
Since it's time, space together, and we are measuring obviously space oscillations, can we assume that we will be able to measure time oscillation in some way as well? Because if time should be stretched the same way as space is being stretched by these gravitational waves.
Yeah, that's an excellent question. I don't know necessarily how we would set up a detector to measure and quantify yes, I would believe that time itself would be adjusted, because space-time is one 4-dimensional non-Euclidean fabric, if you will. And so, but I don't know of a means by which to detect it. And so here's a 40-second animation as two neutron stars slowly decay. So their orbits, energy is being lost through gravitational radiation. These outward perturbations, these ripples in the fabric of space-time, is causing the system to lose energy. And as they lose energy, their orbits decay, and the period of their orbits decreases, frequency increases, until a merger occurs and incredibly pronounced gravitational waves are released. And it's a similar mechanism, slightly different visualizations if you were to look at the merger of two black holes.
What do they become?
Actually, two neutron stars would overcome neutron degeneracy pressure and cross that 2.8 solar mass threshold and evolve into a black hole. It doesn't show that in the visualization, so it's not perfect.
I have a question about sun. Does it mean that someday is going to be also a black hole?
Say again?
About sun.
The sun?
Does it mean that someday is going to be a black hole?
It's too small. And so eventually our sun will swell up into a red giant. It'll actually swell, its solar radius will swell all the way out to almost 1 astronomical unit, or the radius of Earth's orbit. And so the sun will swell up as the fusion reactions change in its core, and the outward pressure increases, while the outer layers are less gravitationally bound to the inner core that continues to collapse. And eventually, due to fluctuations increasing fluctuations in the fusion of helium into heavier elements, outward pressure waves will occur that cause the outer layers to be shed in a planetary nebula. And a planetary nebula isn't quite a supernova, but it's a mass expulsion. It's a large expulsion of mass, like a super solar wind, that then propagates outward, and the white dwarf, the core of the old star, will be left.
And for sure, it's going to change a little bit or more solar system. I mean, this process.
Yeah, it's going to swallow. Now I practice this to impress all the preps. It's definitely going to
We are
eat
going to be alive, I'm sure.
Mercury, Venera, Zemljata, Mars, Jupiter, Neptune, Uran, Pluton. But it's definitely going to swell out to the orbit of Earth. But whether Earth is consumed as the star swells up to a red giant is depending on the increased mass expulsion due to the solar winds. And so more and more mass is being lost, being ejected in the solar winds, that Earth may just slightly slip further and further out in its orbit and may escape a fiery consumption in the outer skirts of the star. But by that time, the Earth will be so incredibly hot on the surface that life as we understand it will not be possible. So, yeah, I want to end on a happy note.